Hello, everyone, and thank you for joining us. Today, we will tell you about quantum orchestration for quantum error correction, a topic which we believe is becoming increasingly important in the path towards large-scale and fault-tolerant quantum computers. So quantum orchestration is a new paradigm for quantum control that we at Quantum Machines are working on days and nights. So we will start by telling you about quantum orchestration, the quantum orchestration platform, that we're developing here at QM, and why we believe it can make an important impact on quantum research and on the quantum community. Then we will discuss quantum error correction, which is the ultimate way to scale up quantum computers. And then we will see how the quantum orchestration platform can help overcome some of the greatest challenges that quantum error correction imposes on the control layer of quantum computers. All right, so we always like to start with who we are, because at Quantum Machines, we are a team of physicists and engineers, all focused entirely on quantum control. We have people on the team who worked on almost any quantum system out there, so superconducting qubits, trapped ions, neutral atoms, spin qubits, quantum dots, envy centers, et cetera, et cetera. And we built the entire company, in fact, because we strongly believe that there must be a new paradigm in quantum control. So the first next question that comes up is, of course, why? Why do we need a new paradigm in quantum control? So we've been working with these quantum systems for many years now, and we all know that in order to do something interesting with these systems, and eventually, of course, have these quantum systems do something interesting for us, we always need to orchestrate a very complex sequence of control and also measurement signals. And this orchestration always must be done by a classical system. And if you go to your favorite quantum computing lab, you most definitely are not going to see such a nice classical orchestra playing music to your qubits. But what you are definitely going to see playing an orchestra of RF pulses to your qubits is a pile of test equipment. So AWGs, lock-in amplifiers, digitizers, signal generators, etc. And this test equipment was, in fact, great for the job of quantum control up until a few years ago. But as experiments started to become more complex, then this test equipment was simply not good enough for the job anymore. And it started to become a real bottleneck, in fact, in the field. So it's no good for labs working on developing the next generation basic building blocks of quantum computers, developing complex control sequences for better control, for better error mitigation, or again, error correction, as we will discuss today. And it is no good for scaling up and building useful quantum computers, large-scale quantum computers, or a system of hundreds or even thousands of control and measurement channels must be programmed in a coherent way and must be fully synchronized, and where classical computation must be done in specialized hardware and where all the modules across the system must communicate with ultra-low latency. So the existing solution simply typically cost years of development. They result in suboptimal systems with sometimes exploding runtimes. No way to perform completely general feedback with completely general processing between measurement and feedback response, something that we strongly believe is going to play an essential role in the future of the field. And we will see that today with quantum error correction, in fact. And finally, and very importantly, it is usually also very difficult and cumbersome to program experiments and quantum programs with the existing control solutions. So this is why we need a new paradigm in quantum control, and this is why we developed what we call the Quantum Orchestration Platform. Now, the platform is a fully integrated hardware and software system that allows you essentially to do three things. First, to run the most advanced experiments, the most advanced quantum programs and algorithms, anything that you can think of, you can run. Second, you can run these experiments on any number of qubits, as the system is highly scalable and modular. And finally, you can do all of this from a super intuitive programming language that we call Qua. Now, okay, so of course, run the most advanced experiments on any number of qubits from a super intuitive programming language. This sounds amazing, but what actually makes this all possible? So first, we developed dedicated hardware. The hardware has a scalable analog front end with analog outputs and input channels for generating control waveforms and also for measuring signals that come back from the quantum system. And where all the channels are fully synchronized with ultra-low jitter and noise performance, phase synchronization, and moreover, many modules can be connected together and can be synchronized so that they can work as a single system. Now, so this is the analog front end in the dedicated hardware. And in addition to that, in the dedicated hardware, at the heart of the hardware, we have the most important part of the technology, which is our pulse processor. It's truly a new processor, not an improved measurement device with better software, but really a true processor, just like the CPU or GPU in your computer, with a full and comprehensive instruction set. That is the language that the processor can digest and run. And it is a new kind of processor, of course, that has an architecture and an instruction set, which we designed specifically and optimized for the task of quantum control. So what does this mean? Well, the processor combines together the 4 elements that must be involved in every quantum control sequence. And these are the following. So the first element is waveform generation. This is generating the pulses that perform the operations on the quantum system. And this includes not only generating waveforms, but also shaping them in real time and changing their parameters like amplitudes, frequencies, phases, stretching pulses, chirping frequencies, etc. This is the first element. The second element is waveform acquisition and processing. So measuring signals from the system and processing them to infer information about the state of the quantum system. This is all done in the pulse processor in real time. The third component is classical processing. And here, this is truly different from any other system out there because you can perform completely general classical processing from tracking errors, performing real-time Bayesian estimation, scanning pulse parameters, etc. All of these are classical processing, in fact, which you can do in the most general sense, as we will see in some of the examples today. And finally, the fourth element is control flow. So if-else statements, for loops, while loops, switch cases, etc. So you can have the most general control flow with branching of the sequence, nested loops, subroutines, and more. Okay. And you can, of course, scale all of this by the number of channels or the number of qubits that you're trying to control. Okay, so this is the pulse processor, and on top of this, we built a programming language that we call Qua. It's a very comprehensive and very intuitive pulse-level quantum control language, and you can write your experiments or the quantum programs you want to run on the quantum device easily in Qua. And then we have a compiler that compiles Qua to the, so that it runs the most efficiently on the pulse processor and gives you the best performance. All right, so later on, Arto will show you an actual demo with Qua, but here's an overview of some of the main components of the language. Okay, so first, we can play pulses to elements in the quantum processor, as well as perform measurements, of course. So these are basically the quantum operations. Okay, so we can play pulses to qubits, we can measure qubits or resonators, etc. Second, we can define completely general classical variables. So like these A and B variables right here. And we can perform completely general classical calculations with these variables. So like I'm doing here, B squared, A equals B squared plus 5. And we can use these variables in our circuit. And this is really what makes Qua unique. It interleaves classical operations and quantum operations in the same code, and it all runs in real time. So this is shown actually in the next point, where we can see that we can use these classical variables as the parameters of pulses. So here we modify, for example, the amplitude or the duration of a pulse according to a value of these classical variables. Now, another critical component is that these classical variables can also be fed by the measurements of the quantum system. Okay, so here we can see that we measure a qubit or a resonator, and the result goes into this classical variable I right here, which we can then continue to process. So you can see here that we say state, which is another variable, actually Boolean variable, equals I larger than some threshold, which is actually state discrimination, quantum state discrimination. And then next, we can do control flow, which again can be based on this classical variable. So for instance, here we can say if state, then we play a pi pulse to a qubit, or while we measure some error syndrome, we keep doing something, etc., etc. So you see now that feedback actually becomes trivial with Qua, since you simply measure your qubit, you store the result in a classical variable, and then use this variable to either affect the control flow or affect the parameters of the next passes you're playing to your quantum device. And finally, we have full timing control with sync and async multi-threading. Okay. All right, so how does it work, or how does it actually look like in reality? So you have your quantum device, whether it's a superconducting qubits chip or a quantum dots-based chip in a dilution fridge, or trapped ions or Tweezers array in a vacuum chamber, or any other quantum device. Then you connect your quantum device to our control hardware, the dedicated control hardware that I mentioned. Each one of these modules right here is called the OPX, and it has the analog front end, as well as the pulse processor that we talked about. And as you can see here, we can also connect many such OPXs, many such modules together, and they actually work as a single controller with a single pulse processor. All the pulse processors are communicating with one another to behave for the user as a single pulse processor. So you connect the controllers to your quantum device, and then the controllers are all connected to our server layer, and then anyone from the server's network can connect and run on the system. Then the first thing that you do actually is to define a configuration file for each setup, or what we call each quantum machine here. So here you see 3 quantum machines, QM1, QM2, and QM3. And once you have defined these configurations of these quantum machines, then anyone, again, from the client computer can connect and can run Qua programs on these quantum machines. All right. So I hope this gives you a broad overview on what quantum orchestration is. And next, we will dive a bit into quantum error correction, and specifically a bit into cat codes-based error correction, and then see how the quantum orchestration platform helps solving some of the control challenges that quantum error correction brings with it. Okay, so as I mentioned, quantum error correction is probably the most challenging task of the quantum control layer of quantum computers. And this is, of course, also a critical task because quantum error correction comes to solve the biggest problem with quantum computers today, which is the very high error rate. So quantum error correction protects quantum information by storing it non-locally in the correlations between the states of many qubits in a way that allows for local errors to be detected and corrected. So, for example, we can encode a single qubit with 3 physical qubits, okay, as shown here. So you see here, instead of storing the amplitudes, yes, alpha 0 and alpha 1 right here, in a single qubit, alpha 0 times 0 plus alpha 1 times 1, we store them in these 2 states of a 3 qubit system. So alpha 0 times 0, 0, 0 state, and alpha 1 times the 1, 1, 1 state. And then, if one of the physical qubits flips, for instance, by some unknown local error process, we can actually correct for it. You can see it pretty clearly here because even though the 3rd qubit here flipped, the majority of the qubits are still in the correct state. But importantly, we cannot simply measure the qubits and do majority voting because this will collapse the state of the system and we will lose the information. So instead, we need a cleverer way to discover what errors occurred. Okay, and in this example, it can actually easily be done by measuring the parity of pairs of qubits. So we measure here the parity between the first and second qubit and the parity between the second and third qubit. And then we see that right here, before the error occurred, the two parities were even. And after the error occurred, the parity of the second and third qubit changed to odd. And so from these two parities, we can actually infer which one of the three qubits flipped. Okay, as long as there was only a single flip, you can see it from this diagram, you can infer what qubits flip. Okay. And more generally, any quantum error correction code uses a Hilbert space with a redundant number of states to define a single logical qubit. So the logical qubit is encoded in a certain subspace of states that have a common value for a certain observable, the so-called error syndrome. Here are the two parities, as we discussed. And the physical errors, moreover, takes the system to a different subspace with a different error syndrome, okay? But without losing the quantum information. So we can then measure the error syndrome and infer the errors, infer to which subspace we jumped and correct. Now, just to note about this example, that the code we're looking at here, which is called a repetition code, is actually not a full quantum error correction code. This is because the repetition code only corrects for bit flip, as we just saw, while in quantum information, there are also phase flips errors. So a full quantum error correction code, such as, for example, the Surface code that Arthur will discuss later on, will show you, it must deal with both these kind of errors, both bit flip and phase flip. And this, of course, requires more qubit and, in fact, more complicated control. But even if we just consider the repetition code, we can already get a good sense of the control challenges that it brings with it. So here is a full scheme showing the quantum circuit of the simplest repetition code, having distance 3, which means it can only correct for a single bit flip. If there are 2 bit flips, we get an actual error. So this is the simplest repetition code. And as you can see, we actually needed 5 qubits because we have 3 data qubits to store the information. And then we have, there are 2 additional measurement qubits used to perform the parity measurements. You can see these qubits down here at the bottom. These are used to measure the parity of the other 3 data qubits. And then we see a few interesting control challenges already. First, measurements must be performed during the circuit, and error decoding must be done in real time. Moreover, this error tracking needs to be repeated and with minimal repetition cycle time in order to improve the error budget, because the error is an error rate. It's the errors per unit time. So if we can make this cycle that you see here that repeats n times in this diagram, we can make the cycle time shorter and keep up with the error tracking and all the gates that needs to be performed, then we can gain in certain cases. Now, another thing that's important is that we typically want to either reset the measurement qubits every cycle or do even fancier adaptive syndrome measurements, which require ultra-low latency feedback and control flow, or classical state machines that run in real time. So again, real-time processing, control flow, etc. Another thing that you see here is that when we correct for the errors, after we repeat this n times, we need to use feedback based, again, on the classical processing that was done in the error tracking stage. So again, Arthur will show you some examples in a bit, but you can kind of see already how these features are exactly the kind of things that are easily expressed in Qua and can run optimally on the pulse processor, right? We have these classical variables that we track the errors with, and then based on them, we decide what pulses we play and so on. You also need to repeat this, by the way, n times. So this is, again, a loop that, again, requires control flow to make the program more efficient in terms of the information that we need to load to the quantum controller. Okay, now the error correction codes that need to be used in practice must use significantly more qubits, in fact, and much more complicated control. So here is some of the figures from the recent state-of-the-art work by Google, where they showed the repetition code with up to 21 qubits, as well as a surface code with 7 qubits. And so there is still some way to go, of course, in order to run error correction code on thousands of qubits, of course. Okay, that's the ultimate goal. And you can see here that the projection error budget for surface code also, so it's still above the threshold that's required in order to gain in logical error rate at the end of the day. So this is extremely complicated. And a very appealing direction that may help reduce some of this complexity came when people started to ask if, instead of using many physical qubits to form a large Hilbert space, one could actually take a single system that has a large Hilbert space and exploit this to simplify things. Moreover, if we take, in fact, the very simple system of a harmonic oscillator, where the energy states are evenly spaced, as shown in this figure here, and by the way, this is actually a system which is relatively easy to make, and there are many ways to do it, like three-dimensional superconducting cavities, mechanical oscillators, etc. So if you take such a system with evenly spaced levels, then even though we may use more and more of the states of the system, we're actually not adding error channels. That's very important, okay? We can see it here, for example, where it is the same photon loss error that takes us from the 3-state to the 2-state, and from the 2-state to the 1-state, and from the 1-state to the 0-state, etc. So this is a point which is worth briefly discussing, because it is actually important to note that using a large Hilbert space of an inharmonic system, okay, with states that are not evenly spaced, is actually, in fact, very similar to using just simply many states of many qubits. In both cases, we need many control lines. You can see it here. In the case here on the left, each qubit has a control line, and on the case here on the right, each transition needs a control channel. And in both cases, also, there are many different error channels. So on the left here, there can be many errors in each different qubit. Okay, each different qubit can have a bit flip or phase flip. And on the right here, each transition can give you an error, right? That you can emit a photon from each different transition. And so in both cases, we actually need to extract and track which errors actually, exactly occurred, and in which control channel we should respond. And in contrast, in the harmonic system, okay, where the states are equally spaced, we have O1 control lines. You can see it here. You can see that we just have, a single control line or single measurement line, and also we have O1 error channels. Okay. So as we discussed, the same photon loss brings us, gives us all these errors, 3 to 2, from 2 to 1, and so on. And this, of course, simplifies lives dramatically, and we will see some examples now. All right, so error correction codes that take advantage of this of such a harmonic oscillator system are called bosonic codes, as they use the bosonic mode of the harmonic oscillator. And we will focus now on a particular type of bosonic code called a cat code, where the logical states are encoded using coherent states or superposition of coherent states. So a coherent state is a semi-classical state, which is an eigenstate of the annihilation operator and which minimizes the uncertainty relations. So this is the closest state to a classical state where both the amplitude and the phase of the oscillations in the oscillator are sort of well-defined. So we can see it. One way to visualize this nicely is using the Wigner function, which is a quasi-probability distribution, allowing us to visualize the state of the bosonic mode in the so-called IQ plane, or the plane of the two different quadratures of the oscillations. So here we see the Wigner function for the coherent state, and we see that while there is, of course, uncertainty in the amplitude and the phase, if we increase the number of excitations dramatically, this becomes negligible, and this is actually a classical state. Now, if this is alpha, the coherent state alpha, then this is minus alpha right here. And if we create a superposition of alpha and minus alpha, the Wigner function looks like this. And actually, this state is the basis for one of the earliest proposals for quantum error correction with cat codes, and where this is the proposal by the Yale group, Zaki Lektas et al. In 2013. The key here is that this state has a well-defined photon parity, which is even parity in this case. And there is another orthogonal state which also has an even photon parity, this state right here, the state on the right. And moreover, a photon loss takes us the two states respectively to two other orthogonal states, both of which have an odd photon parity. So a photon loss takes us from one subspace of the large Hilbert space of the bosonic mode to another subspace, where each subspace has a well-defined photon parity. So we can do error correction. We can define these two states, the state on the left is the zero state, and the state on the right is the one state, and then we can track the parity and perform and correct for photon loss. And actually, this experiment was done successfully by, again, the Yale group in 2016, where the first author is no other than our chief engineer at QM, Nissim Ofek. In fact, this was the first demonstration ever for quantum error correction that actually extends the lifetime of a qubit using active error tracking and error correction. So actually, at the end of the day, extending the lifetime of the qubit using this error correction versus doing nothing. Okay, so for the next part, I'm going to hand it over to Arthur Strauss, who will tell you about another very interesting cat code, as well as show you a quad demo using this cat code example. This code is particularly exciting because it allows, by adding another nonlinear element coupled to the bosonic mode and via clever control again, to stabilize the two coherent states, alpha and minus alpha, and use those as the basis of the logical states. And this so-called autonomous quantum error correction takes care very efficiently of one type of noise, here phase noise, and then one can add a repetition code on top of that and correct also for bit flip. So with that, let me thank you and let me hand it over to Arthur.
Thank you, Jonathan. So hello, everyone. My name is Arthur. So I'm 24 years old. I'm about to graduate as a master's student in physics at EPFL, and I currently work as a quantum software engineer at Quantum Machines. I had the occasion to work a bit extensively with the QOP and Qua, and my goal today is to show you how those tools can be used for quantum error correction with cat codes. So based on what Jonathan just showed you, so the idea here is to realize that the most important noisy quantum channel in a cavity that was taken care of was single photon loss. But now the next level was to think, okay, what are the other noisy quantum channels that could occur on a single cavity? And the answer was, well, there could be any kind of local noisy process in phase space that could actually make the state get out of the manifold spanned by the coherent states themselves. And the question was, can we kind of engineer some kind of interaction dissipation process that would secure the cavity in this manifold? So the answer brought here was to actually bring up two-photon dissipation and also change the encoding of the coherent state themselves. So I will quickly share the screen to show you the external block sphere to show you the difference about what you can see. On the left is the encoding that Jonathan just presented before, which was dealing with a single photon loss extensively. Whereas what I'm about to talk now is the error correction cycle happening on the block sphere on the right, which basically encodes the logical states 0 and 1 onto the coherent states as opposite phases themselves. So as you can see now, the 0 state actually becomes the plus alpha, whereas the 1 becomes the minus alpha. And here you recognize that the plus and minus are nothing else than the Schrödinger cat states, which basically bear the name according to, as Jonathan mentioned, those alpha and minus alpha represent classical or semi-classical states of light. And here we have superposition, coherent superpositions of classical states, exactly like the thought experiment of Schrödinger, which was superposing two states of the cat, which are macroscopic definitions, which are dead and alive. So that was for the historic part. So let me come back to the presentation. So here, the idea was to consider the mechanism that would deal with two photon dissipation. So why do we do that? It's because if we can engineer such an interaction, we can actually engineer a specific device where the coherent states alpha and minus alpha become steady states of this master equation that you see here. So that works well, but what does it give in practice? So in practice, so this was the experiment that was conducted by Raphael Lescan and Zaki Lektas last year. And it's basically engineering from scratch this interaction between the storage mode and two other elements that we'll introduce right now. So the first other element that we have is the buffer mode. So it has the property of carrying a very high loss rate and is basically driven by a weak microwave drive. So this buffer, which is essentially another cavity, exactly as the storage mode itself, has two main roles. So the first one is it's the role of the carrier of the photons that will go through the cat, because you want to make sure that you can engineer a process that will only exchange photons by pair, because of the relation given by the master equation you see above. So this is the first mission. The second role of this buffer is actually to evacuate all the entropy accumulated in the system regarding to the photons that will be given away by the cavity, because of course the storage mode has a loss rate. And what we would like to bias is that we want to replace as much as possible the single photon loss rate towards the two photon loss rate, so that we can preserve the encoding of our state into the cat qubit paradigm. So this very high loss rate conducts the buffer to evacuate towards the environment very quickly all the photons that are received from the storage mode. And now, okay, how do we engineer in practice this two-photon interaction? Because it's not obvious that this coupling induces a nonlinear interaction between the buffer modes and the storage mode. So this is where we introduce the ATS, which is a contraction for a symmetrically threaded squid. So this device is essentially a set of Josephson junctions, which have the property to couple nonlinearly the modes of the cavity, the storage cavity, and the modes of the buffer. And through this nonlinear interaction, we are indeed able to privilege this kind of two-photon exchange process. As you can see on the figure, it goes in both directions. And of course, we want to control as much as possible the incoming flow of photons and the incoming flow of photons to maintain the coherent state as stable as possible. But also, we want to control the output flow, which will stabilize the code word. So now, the main idea. So the main idea now regarding this strategy is the following. So we can move for a second into the semi-classical approximation, because alpha being the value of the coherent state, it's also the expectation value of the annihilation operator. So on average, how many photons do I lose? So in this picture, we can see this two-photon dissipation process as a pseudo-potential, which has the forms of two different wells. So on the left part of the figure, you can see that those two wells can be either very close, so very undistinguishable, but they do benefit from two attractors. And the positions of those two attractors are respectively alpha and minus alpha, which constitute the basis of our own encoding. So the problem is okay, we know that through this potential, all potential errors that might occur in phase space will eventually fall back to one of the attractors. But there is a non-zero probability that it will fall back on the wrong attractor. Like, for example, if I start in the zero state, so in the alpha well, if I escape temporarily this manifold and I eventually come back through the potential to the minus alpha, I will recover a logical bit flip error, which I want to avoid. So how can we overcome this logical bit flip that might occur by tunneling or some phase errors? We can basically go to the shift to the figure on the right and just see that we increase the value of alpha. And increasing the value of alpha basically increases the distance in phase space between the two wells. And so you make a further distinction between the two attractors. And this has for effect eventually to induce an exponential reduction of bit flip errors with respect to the cat size, where the cat size is the absolute value, the norm of alpha, essentially. So in the end, we have this exponential reduction of bit flip errors, but of course, this does come at a cost. And this cost is the increase of phase flip logical errors, which are nothing else than for single photon loss channel. Of course, when we increase the cat size, it means that we overall increase the number of photons inside the cavity. So we increase the probability of having single photon loss, which yields, in our own code word, logical phase flip errors. But we shall see that the repetition code or the surface code that I'm going to introduce later is going to try to be biased towards these phase flip errors, where we're going to care much more about correcting actively those phase flip errors, whereas this autonomous scheme of two-photon dissipation plus the big cat size can prevent us from caring about any remaining bit flip errors. So now let's shift to the demo. So I will take the same experiment, and basically the first experiment I wanted to showcase is to perform vignette tomography on this cat qubit that we'd like to characterize. So here, as Jonathan presented it, you have two OPXs that are presented here, and you can identify the channels that are required to control all the elements. So as I mentioned before, you need elements to control the drive, to impose a microwave tone on the drive. As well, you have to do a pumping tone on the ATS at a specific frequency. And of course, if you want to be able to do vignette tomography, you will have to perform displacement operation, not the storage mode. And finally, have control of a transmon and a readout resonator for performing parity measurement. So, okay, let's delve a bit more in how you do parity measurement in vignette tomography. So the circuit you see on the left is the quantum circuit that is necessary to operate the parity measurement of the cavity. So this parity measurement is necessary to construct the vignette function, and it's basically relying on the dispersive Hamiltonian, which characterizes the interaction that occurs between the storage mode and the transmon qubit. So this interactions allows the computation of the conditional phase operation shown on the right hand side, which eventually involves the parity operator. You can identify the conditional phase that occurs upon the excited state of the transmon as the parity operator. And once we deduce the value from the parity operator, we can basically reconstruct for any point in phase space, according to the ability to perform a displacement operation, we can reconstruct this vignette function and eventually recover the parity by doing this mapping on the transmon states. So yielding an excited state from the transmon will lead us to the conclusion that it was an out parity and ground state to an even parity. So now let's go over the Python for a second. So I will show you the first script doing vignette tomography. So I will share the screen. Okay, so as Jonathan showed before, Qua is a very intuitive programming language. And again, control flow is super important. And for vignette tomography, what we want to do is actually perform this parity measurement multiple times for various displacement operations. So summarized as follows. We have here three main loops that we incur. The first one will only be considered for getting statistics. So we put it outside typically because it's we have the ability to perform super fast and easy averaging within Qua using a feature of what we call the stream processing. And here you have two loops that will roll over the real and imaginary part of alpha. Now let's pay attention to the code. So the experiment shall start by a state preparation. So the tomography of the state we want to characterize. So in this case, I will just play a tone on the ATS, apply a tone on the drive, such that I will prepare eventually the plus state in my encoding, because it's the solution. It's the steady state of the master equation I showed before. And once I prepared this state, I can start dealing with the circuit I presented just before. So I will place my displacement operation, and which, as you can see, is going to be modulated by an amplitude given by the I and Q parameters, which are actually part from the loop. And I would like to stop a second there to basically pinpoint an important feature of Qua. Here, as you can see, the operations that are being played are the ones that are going to be uploaded in the configuration as a list of operations, as a baseline, basically, for playing operations. But what you see here, this amplitude modulation, you do not need any additional loading time. This is happening in real time. The pulse processor is able to tune up in real time the baseline operation that you provided and tune up its amplitude. And you can actually tune up much different features, like its duration, its overall length, and even its phase and its frequency. So you can do everything in real time without any latency. And so this is a huge economy of loading time, because in a regular AWG, what you would do to perform this vignette tomography is to load every single waveform for every different amplitude. Whereas here, it's as simple as playing the baseline and just modulating it in real time. The processor will take care of it for you. Once we have done this displacement operation, here I can define a Ramsey operation, which is because we call this Ramsey because it's usually this Ramsey sequence that we play on the transpond. And actually, as you can see, the fact that Qua is embedded as a context manager, so as you can see here, the structure is a context manager in Python, I can easily define some macros, which is essentially Qua functions, outside of the code. And this makes the code very modular, and you can actually involve a lot of Python structures up to compilation time for helping you write your programs. And this is how you can conceive much more complicated algorithm. So now, there is another experiment that we can derive from this vignette tomography that I would like to show you. So I will come back to the slide for a second. Basically show you that out of this vignette tomography, we can actually do some kind of calibration experiments. So in the paper of Zaki Lektas and Rafael Lescan, this experiment was conducted to basically calibrate the amplitude of the buffer drive. Why do we want to calibrate this amplitude? It's because we have a constitutive relation between the value of alpha that will characterize the coherent state in our cavity and eventually the amplitude of our microwave drive. So to do that, you can see on their experiment that what they provide is you prepare the state, you perform vignette tomography for one specific amplitude, then you calculate the distance you did, the distance between the two alpha and minus alpha blobs. So to estimate basically the value of alpha that you set up according to this amplitude, and you repeat it for many amplitudes, which gives you the graph that you see on the right. So in Qua, I will show you how you can easily extend the script I just showed you before. In one single line, I can actually increase dramatically the performance of the to rewrite the experiments to make it comply. So here I will basically add another for loop. So here I want to loop over what? I want to loop over the amplitude. So let's say I want to start with an amplitude of 0.1. Let's say that I also had configured before a maximum amplitude target. Then I will establish a step. So a step which might be d epsilon in this case. And what I want to do is, okay, so everything will be repeated for this specific number of amplitudes. And the only thing I have to do here is to basically modulate the amplitude of the drive that is applied on the buffer. And this, again, I can do this dynamically, as simple as this. And so that's it. In 2 lines, I have extended the single vignette tomography experiment to actually a calibration sequence that can make me retrieve all the results super easily for performing this calibration experiment. To give you a comparison for an AWG, so you would have to multiply for each of the loops that you have here, you would have to multiply dramatically the number of waveforms you would have to load. We checked with one customer how much time it would take to load all of this for creating a grid of, for example, 40 points by 40 points. It might take approximately 10 hours to run the full experiment, whereas in the OPX, it would take about 1 hour and a half. Essentially, so you get much more than 5 times the time you would spend with a single AWG, and on top of that, you gain super readability and ease at writing the program itself. So now I will shift to the second part, which is now combining what we've learned before and synthesizing the active quantum error correction part associated to the surface code and the autonomous quantum error correction related to the scheme with the cat codes. So here, AWS has been following this lead in a proposal that they published last year, at the end of last year, essentially. And here, the principles are basically the same, except that this time, the architecture is relying on one buffer, buffer plus ATS combination, which we're going to call from now on the reservoir. And this reservoir is not going to be in charge of tuning up one single storage mode, but to control many of them. So the reservoir has 2 functions in this case. It's used for the stabilization against to prevent bit flip errors, logical bit flip errors, but it's also used to perform control, active control, so quantum gates, essentially, on all the storage modes. Now, the question is, how do we address those storage modes independently? This technology used here is the frequency multiplexing. So we can do that easily in Qua as well. I will show you in a second how we can perform that. So the frequency multiplexing is because each of the storage modes that is going to be present in the cat code, in the surface code architecture, is going to carry its own resonant frequency. And depending on the frequency of the tone you apply, you will be able to address individually each qubit. So now let's shift to the setup. So here I want to show you basically the syndrome extraction of one plaquette measuring one X-type stabilizer. So an X-type stabilizer is basically the to detect phase flip errors, right? It's an inverted order, like where Z stabilizer would try to detect bit flip errors, whereas here in the X-type stabilizer would try to figure out about phase flip errors, which are the most frequent errors in our system, right? Because we created a bias. And so here, as you can see, we have two reservoirs, which are going to address 4 data qubits and 1 ancilla in the center. So on top of that, I should mention that there is also to this plaquette a transpon and a readout resonator that will serve for the syndrome extraction and the parity measurement, which works exactly as we've seen before. So here the error detection scheme goes as follows. So you can see on the right upper corner the layout of the drawing. So the blue circles represent the reservoir. So you have 2 of them, and the data qubits are shown in gold, whereas the ancilla qubit is shown in gray. So here you can see that we want to conduct a bunch of C0 gates, right, between the ancilla qubit and those data qubits. And at the same time, we also want to perform some kind of parity measurement by using another device, which is called the phononic readout mode, which is nothing else than a storage mode, which is this time not stabilized by the ATS. It's an independent mode that will serve only for the readout scheme. So without going too much into the details, I would just like to pinpoint here about what Jonathan mentioned about the need for active reset and ultra low latency. You can see that you require for the transpon and a reset of the qubit at each iteration, and using Qua and the ultra low latency feature of the OPX, you can actually reduce significantly the time you need to perform this reset, which provides you, which gives you the opportunity of increasing the number of measurements that you can perform, and then improve your fidelity on the syndrome extraction. And of course, you want to do this measurement scheme simultaneous to the next cycle of error correction, which would begin in playing again C0 gates in a row. To give you an insight, C0 gates on this architecture would last around 1 microsecond approximately, whereas the latency required to do active resets is about 200 nanoseconds. So if we forget about the measurement, like we could hope to do up to 3 or 4 measurements in a row before having to come back to come to the next cycle of error correction. Finally, so here, of course, we focus on the active error correction part, right? So this is really the surface code, which is focusing on detecting phase flip errors. But also, we should keep in mind that additionally to that, we also have this stabilization process that occurs in the back end with the same reservoir. We have this pumping of the ATS that will try to maintain all our code space in the right manifold. Our state in the right manifold of coherent states. And so this is the schedule that that is shown so that we can basically stabilize two modes at the same time and also perform active error correction. So as you can see here, we summarize the combination, the hybrid combination between active and autonomous quantum error correction using the same device, which is the reservoir. So, okay, so I will just flash the code briefly to show you exactly what it is about. So I will not suspend, as you can see, there are lots of challenges going on. So I will briefly show you the code, how it works. So, just wait for a second. Yes. So as you can see here, the program stands very simple. So we want to have a run of X stabilizer scheme and perform a set of readout. And we want, of course, to repeat it multiple times to repeat the syndrome extraction. So without going into too much details here, this stabilizer scheme goes at the same time with a CNOT gate, which is active error correction, and a stabilizer scheme that is required for autonomous quantum error correction. Yeah, if you have any questions about this, I will be happy to answer by email. I think I will wrap this up so I can elaborate on the end of the talk. So let me come back here. Yeah. So okay. So as a summary, as you can see, the QOP and Qua feature many different answers, present many different answers to multiple challenges that are related to error correction with cat codes. So we have the phase synchronization between many channels, the fact that we have to relate the amplitude and the phase of the drive to make sure that we set up the right coherent state. We are able to do also phase modulation in real time, and this is necessary to compute the CNOT gates so through code space deformation, which is actually a pretty interesting feature. Again, we have also this notion of frequency multiplexing, ultra-low latency feedback to cover this active reset and the increase of fidelity for the readout. And finally, the error tracking, which requires lots of classical processing that can also be done in real time within Qua using all the flow control that Jonathan showed earlier. And with that, I think I'm done. So thank you very much for your attention, and hope like it was a nice example to show how you can really imagine quantum error correction to be a major challenge in the next few years for quantum control, and also exciting times for reaching out for fault-tolerant quantum computation.
Well, thank you, Arthur and Jonathan. We have time for a few questions, and don't worry if we don't have time to get to your question, check your inbox. So here's one interesting question. Do you need one dedicated pulse processor box for each single qubit you need to control?
No, so as Arthur showed, it depends on the quantum system that you're trying to control. Typically in the superconducting qubit setup, one would use a single box for a few, between 2 to 4 qubits. In different architectures, different types of qubits, this could go even up to 10 or 20 qubits per box, for example, in with array setups, etc. So it really depends on the number of channels you need to control your quantum system.
So this one seems like a philosophical question to me. Is your pulse processor, in effect, a translator between digital and analog computing?
So I wouldn't say it exactly like this because it's true that the processor translates essentially information in digital form, essentially sends it to the analog front end to be translated to analog waveforms, but it's not translating digital quantum computing commands to analog quantum computing commands. It's actually a pulse level control language. So in fact, you could, using Qua, describe both analog quantum computing as well as digital quantum computing if you calibrate pulses to gates, and this allows you to do both. Okay.
So possibly a related question. Does it support real-time digital I/O, for example, to adjust experiment sequence in real time depending on some digital values fed from outside?
So yeah, I could take this one because I worked extensively on this. So yes, we do benefit from input-output variables. And actually, I can think of a very useful context for this is hybrid classical quantum algorithms. When you think about those algorithms that need an outer loop to function, you usually want to optimize parameters outside of the program, like you retrieve some kind of cost function evaluation from the quantum computer. You want to optimize your parameter and feed back those parameters to basically rerun a quantum circuit dependent of those parameters. And actually, you can do that pretty efficiently without having to reload a new program at each iteration. You have this communication, this back and forth communication between what we will say the client PC and the OPX very seamlessly.
And maybe I can just add to that also that we also have in the hardware digital inputs. So another hardware can basically send digital signals to the to our hardware and communicate with it as well. So you can feed the pulse processor with digital signals from different hardware.
So another question, how does parity measurement not destroy the state? I mean, how different is that from measuring the bit? So okay, so that's sort of the essence here of quantum abstraction is that when you perform these parity measurements, you're not destroying the states because you don't gain the information. So if you notice the two states we use, for example, in the repetition code was 0, 0, 0 and 1, 1, 1. Now, if you notice that the parity between, let's say, the first and second qubits is even both in the 0, 0, 0 state and in the 1, 1, 1 state. So when you measure the parity, you don't collapse to one of these two states because both of these two states have the same parity between the different qubits. So you gain the information on the error, but you don't collapse the state to one of the two logical states. And that's how we can preserve the information. So I think this is going to be our last question. How much time is gained when performing real-time amplitude modulation for vignette tomography compared with the usual arbitrary waveform generation?
Essentially, when you want to do full AWG-based compilation of all those waveforms, for one vignette tomography, when you want to build 40 points by 40 points, the load time that you would expect would be around 2 to 3 hours. If you want to expand for multiple amplitudes, it can go to more. Whereas in the case of the OPX, when you do compile just this baseline and play real-time amplitude modulation, you have nearly no latency. So it's just dependent on the runtime of all your pulses. You spare yourself the economy of doing all the uploads of the waveform.
Yeah. Also, Arthur, you were so quick. We can squeeze in a final question.
Yeah.
So you mentioned something called synchronous and asynchronous multi-threading. Does it have to do with controlling multiple physical systems like qubit chips, or does it have to do with something else?
It could have to do with also multiple controlling multiple chips, but it gives you the ability to create these threads in the program. Each can play pulses and so on, and they could be you could do it in parallel, and then you can synchronize these threads within the Qua program. So that could allow you to both, for example, program many different channels that are used to program the same quantum system. Sometimes you need different channels to do different things, of course, play different gates, go into different subroutines, etc. So you need this asynchronicity and synchronism even when you're trying to control a single system. That's very important. But also, if you want to control multiple systems, you can use that feature, yes.
So thanks, Jonathan and Arthur, for a wonderful, interesting webinar, and thanks everyone for listening. This webinar is now over.
Thank you, Charles.
Thanks, everyone. Thanks, Charles.